Here's a chance to practice a force problem. You'll recognize this problem as coming from the lab. So I'm going to ask you to read the problem, pay attention to the guidelines for problem solving, think about general problem solving strategies, and see if you can do this problem. If you have any difficulties, you can pause the video and see what I'm doing, or you can proceed along with me as you solve the problem. Okay, if you're checking in, you should have done a diagram. And notice I put in my x and y coordinates, the angle, then I did a free body diagram. I took the block all by itself using the same coordinate system, lined up with the track surface, and put in all three forces. The friction force is along the track going up, slowing it down. The force of gravity has x and y components that are the sine of theta, cosine of theta, where theta is the track angle of 36 degrees, and the normal force is drawn carefully perpendicular to the track and labeled n. So look at the diagram, look at the free body diagram, and see that you got it all right. Then the third step is the equation. Of course, we start with Newton's second law. We separate it into the two vector equations, and we proceed from there. So if you're good this far, continue. If not, make the changes that you need to make. Once again, the formatting is essential, so make sure you've done have all the details that I have in this figure. Okay, my writing on this tablet isn't great, but you can see that I did some of the forces x and some of the forces y directly from my free body diagram. So let's do y first. Is n minus mg cosine theta equals 0 because there is no acceleration in the y direction. And that gives me this simple result of n equals mg cosine theta. In the x direction, the force going down is the mg sine theta. The force holding it back is the friction force. That's all written in here, mg sine theta minus the friction force equals the mass times the acceleration. And notice that I have down the ramp is positive. So doing the algebra, substituting in the friction force is mu kn, substituting mg cosine theta for the n, and then when I get to this equation, I divide all the terms by m, and I'm left with ax equals this, factoring out the g. So you should do all that algebra, and then I don't show on your work, you should put in the sine of 36 minus 0.24 times the cosine of 36 times 9.8 meters per second squared, and come up with this answer. And if you were asked for this answer, you would round to 3 significant figures, but we're going to use it in a calculation to complete the problem on the next page. So try finishing the problem on your own before you check and to see what I did. Okay, final check. We used this equation, as we often do in lab, to relate the acceleration to the distance and the time. And so doing the algebra, I get this equation. And given that I already have the acceleration from the other page, I could just come down here and write it out this way and get the time. But if I wanted a general solution like we did in lab, we could set the acceleration equal to this and equal to what we got on the other page for the acceleration, and then solve for t. And our solution for t, the general solution for t, looks like this. We put the numbers in. Notice I put in numbers with units. I cancel the units. We're taking the square root of 1 over second squared. That's the square root of second squared, so the units do come out to be seconds. and the time comes out to be 0.72 seconds, a pretty short time. Let's check our answer. Does that make sense? Yes, it makes sense. We know from lab that at a coefficient of friction of 2.4, an angle of 36 degrees would be quite high. And so the acceleration at 3.857 is pretty fast. It's going to go 1 meter in a fairly short period of time. So we can be confident the answer is probably correct.